4.4 Relationships. Okay, example number one. Data on the height of the corn each week was collected to see if there was a relationship between time and height. The data collected are shown in the table. So here in the table I have length of time in weeks and the height of the corn after each of these weeks. Okay, so part A asks us to what is the independent variable and what is the dependent variable. So the independent variable, usually it's on the left, but it is always in terms of what would count as independent variables. So things that are countable, arbitrary, controllable. Okay, sometimes time is usually what we would say is an independent variable because time is just it's discrete numbers. It's 0, 1, 2, 3, 4, 5 seconds, weeks, hours, minutes. Okay, it's something that is that we can use as a base, right? It's just something that we can control. We can control how much time we're studying something. Okay. The dependent variable would be a variable that depends on that independent variable. So the height of the corn, right? The height of the corn, the height of the corn could be anything, but it really depends on what time of the week has that life of that corn has reached. So that usually would determine its height. Right? It grows through time. So here I'm going to say independent is my time, and the dependent is my height. Dependent. Yeah, there you go. And the independent variable we classify as x, and dependent we classify as y. Okay. Okay, so independent variable here is length of time. And the dependent variable here is the height of the corn. All right, let's move on. Part B, make a scatter plot of the data using the grid above. So I'm going to use this grid. I'm going to make a scatter plot. Now, in any scatter plot, you should have your labels. So this is a data on corn growth. I'm going to make a title that says corn growth. My labels for my axes are going to be time for the independent axis, time in what units. It's going to have to be weeks, so make sure you include your units. And on the y-axis, my dependent variable is height, and that's what I'm going to write there, and my units for height is centimeters. Now you have to create a scale. Now if my number of weeks goes from 0 to 6, so I start from 0, it makes sense. Maybe I can make every square equal to 1 week. So 1, 2, 3, 4, 5, 6. And I know I'm left with more space, but sometimes maybe we need to pick a prediction. So I can extend that as well to higher numbers. Now the height goes from 0 all the way to 70. So I need to make sure that I have enough room for 70. It looks like I can make every 2 grid squares 10. So if I made this one here, this would be 10. Count 2 more and I'd have 20. Then 30. 40, 50, 60, and 70. That's more than enough, and I still have enough room left over to even make higher prediction values if I needed to, so 90, even all the way up to 100. Okay. Now it's important that you make the scales even. You never want to make a scale where it's like, oh, I'm going to make one grid square 0, the next grid square 5, the next one 18, the next one 29. That doesn't work. Okay, that will always give you they'll always, like, you just don't make the values here as part of your grid, like exactly your grid scale. Although you have to have even spacing for your grid scale. That's why I'm evenly counting by tens every 2 squares. Okay. Then we put the data into our grid based on this scaling. Okay. So for 0 weeks, we have 0 height. There's our first point. After the first week, we have a height of 5. So there's my next point, halfway between 0 and 10. The week after that, I have 2 and 18. So at 2, I go up to 18. Again, now this is the thing. So we don't have 18 on the graph. We have to go close as possible to 20, but not actually touching 20. Okay. Then we have 3 and 29. So again, the idea is we're not going to have 30 yet, but just under 30. 4 and 45, so halfway between 40 and 50. 5 and 59, so another point just before 60. And 6 and 70, so here's a point at 70. Okay, so we have some points. Doesn't quite make a straight line, but it does look positive. Okay, so part C, it says, finish the following statement to describe the relationship between time and height of corn. As the number of weeks increases, the height of the corn increases. So as time increases, height also increases. This is a relationship that is a positive correlation. If possible, sketch the line of best fit. And that's what we're going to try and do now. So let's try and make a line of best fit, a mathematical model for this data. So let's create a line. Here we go. And let's try and draw a line, something like, I'm not going to be able to get all, I'm not going to be able to cross all these points, but you want to try and touch as many as you can. So if I did something like this, I'd touch 3 points, but I'm leaving too many points below the line. You want to have an even balance of points above and below. So I might not be able to touch as many points. So maybe something like this would allow, just slightly the same amount of points above and below, kind of thing. Okay, this might be a better line of best fit. So, oops, what happened to my? So again, you're not going to get this always perfect, which is why we use computers to do these things. But you just try and do your best estimate, trying to stay under the guidelines and the rules I try to create to create lines of best fits. So right about here, let's just keep that. Okay. And if you ever need to make predictions, maybe you need to increase the length of the line as well. So you can also do that. For some reason, it's not letting me manipulate. Nope. There we go. So I can extend the line if I need to, like that. All right, there's my line of best fit, and I was able to sketch it. Part E, determine the number of weeks if the height of the corn is 30 centimeters. So at 30 centimeters, let's zoom in back on our graph. We don't have a data point here. There's no data point on my table. Height of corn. Where's my 30? 29 is not exactly 30, although it's a good estimate. I'm going to use my line of best fit. So at 30, we're going to our line, and it looks like we reach about 3 weeks approximately. So, about 3 weeks, you get 29 centimeters. A little, just tiny bit over 3 weeks might get you to 30. Okay? So based on the line of best fit, I'm going to say here, so based on the LOBF, line of best fit, it's 3 weeks approximately. And again, lines of best fit are always approximations. We're not using them as a way to tell us exactly what the number is. It's just a good way to predict something. Determine the height of the corn after 10 weeks. Is the prediction reasonable? So again, our data only goes up to 6 weeks. So to get to 10 weeks, we have to make a prediction using our line of best fit. So at 10 weeks, if we go to 10 and go all the way up to our line of best fit, it doesn't even reach. It's going to be beyond. It's going to be beyond 100 centimeters. Okay. So it's going to be greater. It's going to be more than 100 centimeters. You can't say exactly what it is. Maybe 115. Okay. So based on a line of best fit, greater than 100 centimeters, maybe 110 to 115. Okay, but is this reasonable? Yeah, we can say it might be reasonable. Yes. Okay, but at some point the corn will stop growing. Okay, so it's yes, but at some point corn stops growing. Okay, who would want this information? Well, farmers would, definitely. Why would they want it? Maybe they want to know when they need to put seeds into the ground. So when to seed. So they know that after 6 weeks or 7 weeks or 8 weeks or 9 weeks or 10 weeks they get the corn, they can plan when to plant their seeds. And buyers might want to know this as well because they want to know how long to wait. How long does it take to wait for corn to reach the market. Okay. If scatter plots show the height of the corn did not change in 4 weeks, might the farmer be worried? No, because corn can stop growing when it is time to harvest. So no, the corn can stop growing when it is time for harvest. Okay, example number 2. The data below represents the values of a vehicle after different amounts of time. Okay, so what's the independent variable and what's the dependent variable here? So the number of years after purchase is the time value. That's going to be my independent variable. The approximate value of the vehicle, so the value depends on how much time has passed. That's my dependent variable. So this is going to be x, that's going to be y, dependent on my right, independent on the left. Okay, so make a scatter plot. Here I'm going to put number of years on my x-axis, so number of years, and the value in dollars in my y-axis. Make a scale, so it's reasonable to count the number of years by 1, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and dollar values, what's my biggest dollar value here? 28,000. Maybe it's reasonable to count by 5. So 5 every 5,000 here. So every 2 squares is 5,000. Here's 5,000. Here's 10,000. Here's 15,000. 20,000. 25,000. And 30,000 up here. And that leaves still a little bit more room to grow if I need to, but it looks like the prices are decreasing, so maybe I don't need to. I could have made the scale a little bit bigger. Okay, and then part C says, describe the relationship between the number of years after purchase and value of the car. Well, I still have to plot my points, so I forgot to do that. And I forgot to put a title, so don't forget to do that. Value of the car is going to be my title. And now I'm going to plot the points. So at 0, the car is worth 28,000, so just under 30,000 over here. After 1 year, it's down to 24,000. After 2 years, it's down to 18,000. After 3 years, it's down to, after 3 years, it's down to 21,000. All right, sorry, 1, 0, 1, 2 years. After 3 years, it's down to 18,000. If that was right, it's didn't put the right place. 4 years, it's down to 14,000. And then 9,000. And then 5,000. After, I'm not even looking at the X values. So 3 years, it's 18,000. That was right. After 5 years, it's 14,000. Notice we're skipping some X values. 8 years, it's 9,000. 10 years, it's 5,000. So we're down here. Okay. And I'm going to need to create a scatter line of best fit. So I'm going to try doing that now. And here's my line of best fit. Bring it down a little bit. Okay. So 3 points below, 3 points above, one kind of touching it. That works. Okay, so let's go down to the next question. So part C, describe the relationship that we see. Well, it's a negative correlation. The points are going down. Negative correlation. We have a downward trend. And we can say as the years go up, the value of the car goes down. Okay, so we made a line of best fit already. Determine the value of the car after 4 years. So after 4 years, here's 4. We don't have a data point for 4, but we can use the line of best fit to make an interpolation. And it looks like the value of the car would be between 15,000 and 20,000, about halfway between, so 17,500, based on our line of best fit. So based on line of best fit, $17,500. Determine the number of years after purchase such a value of the car is 0. Is this prediction reasonable? So if you look at my line of best fit, I extended it down all the way to $0, and it says after 11 and a half years, between 11 to 12 years, so definitely by year 12, it's going to be worth $0 if I follow the line of best fit. So if I settle halfway between 11 and 12, then I'll just say 11.5. So 11.5 years is when the value of the car is going to reach zero line of best fit. But does that make sense? Is that prediction reasonable? No. The car cannot have a $0 value. The value of the car is always greater than zero. And the reason why is because the car, as long as the car exists, even if it was beat up, it still has metal in it, and it still has valuable metals that can be resold and recycled. So there's definitely some value left in the car. So this graph would most likely taper off at the end towards zero, but it can't be zero. Who would want this information? Well, people who buy and sell cars, so dealers and buyers. Okay. And what are some other factors that might affect the value of the vehicle? So list some factors. So none of you are driving cars yet in grade 9, but if your parents do drive cars and they've seen what they experience, so mileage, how many kilometers you drive your car, that affects its life. Any damage to the car, have you been into an accident before? That would also affect the value of the car. How in good condition, is it rusting? Is it still shiny? What is the make of the model of the car? Some cars are more popular than others. And color. Some people are also partial to colors of cars. So those are just some factors. There are other factors as well. But those are just some factors that could change the value of the vehicle. Okay, and that ends this lesson. 2 examples.